Hello and welcome back. In the previous video, we discussed how you could handle circuits that involve multiple resistors by treating these resistors as behaving like a single equivalent resistor. And while this is a really useful way to study these types of circuits, it doesn't give you a full picture of what's going on because you can't actually see what's going on inside this equivalent resistor. In other words, you can't calculate the amount of current that's flowing through each part of the resistor. And in order to get at this type of a thing, we need an additional set of rules which are collectively known as Kirchhoff's laws. And the first rule that we have is something called the junction rule. And basically, what the junction rule is it's kind of like the continuity equation for water flow, but for current instead. And what the junction rule says is that anytime you have three or more wires that meet up at a point, for example, if I have something like this point right here where these wires meet is called a junction. And what the junction rule says is that the current that flows in to the junction has to be equal to the current flowing out of the junction. So for example, I have a junction right here which has 5 amps flowing into it. So looking at this, because there's 5 amps flowing in, there's 3 amps flowing out through this branch, we can see that the bottom branch of the circuit must have 2 amps flowing through it, so that the current that flows into the junction is equal to the current flowing out of the junction. The second rule is called the loop rule, and basically the idea behind this is that the voltage at any particular point in a circuit can only have one value. And what this means is that suppose I consider this point right here, and suppose this point A has a voltage of 0 volts. And now let's suppose I go around the circuit like this in a sort of clockwise fashion, and I calculate the change in the voltage over each of these circuits. So I'm going to gain some voltage as I go over this battery, and then I'm going to lose some voltage as I cross this resistor, and when I get back to the point A, the total voltage change that occurs as I go over the battery plus the voltage change as I go over the resistor has to be equal to 0. Because if the voltage change is not equal to 0, I'm going to wind up with 2 different values for my voltage at point A. Because I started out with, say, 0 volts at point A, and then as I go around, if I calculate that voltage change, I would wind up with a different voltage for point A. And remember that voltage describes how the potential energy would change if I added a charge to this point in the circuit. So obviously the energy is going to change by the same amount if I always add charges to that particular point. So the voltage at point A can really only have one value. And so that's why the change in the voltage whenever you go around a closed loop has to always equal 0. And these two rules together, the junction rule and the loop rule, are collectively known as Kirchhoff's laws. Now, one important thing about applying Kirchhoff's laws, which we already saw in the example we looked at with the junction rule, is that in order to apply Kirchhoff's laws, we have to denote the direction that the current is flowing through each of the wires inside the circuit. Now, in some examples, you're not actually going to know the direction that the current is flowing through each of the individual wires. However, all you need to do is guess the direction the current flows through each of the wires and draw a little arrow in the circuit diagram to indicate that direction. Then if you apply the junction rule and the loop rule, you can solve for the currents. And if you calculate a negative current when you solve these equations, it just means that the current is flowing in the opposite direction than the direction that you had guessed. Another important thing about applying the loop rule is that if we think about this circuit down here, is that when current flows through a resistor, the voltage decreases. So that means that here in this example I have at the bottom of the screen, the current is flowing from point A to point B, which means that the voltage at point A is lower because the voltage decreases as we move from left to right. So sometimes when you're applying the loop rule, you'll have to calculate the change in the voltage as you go in the opposite direction that the current is flowing. So for example, if I want to calculate how the voltage changes when I go from point B to point A, the voltage will increase because the voltage at point A is higher than the voltage at point B. So in this case, the voltage increases by an amount given by Ohm's law. So this is a little bit of a tricky type of a thing that sometimes throws students off when we start applying the loop rule. Now, I feel like the best way to understand how we apply Kirchhoff's laws is to look at a couple of examples. So this example, we're given a circuit over here on the right, and I'm just asking you to write down the equations that you get from applying the loop rule and the junction rule. So starting with the junction rule, if we look at this equation over here, there are two junctions. There's the junction over here on the left and another junction on the right. Now remember, the junction rule says that the current flowing into the junction has to be equal to the current flowing out. The current that flows into this junction is equal to I3 plus I2. So we have I3 plus I2 has to be equal to the current flowing out of the junction, which in this case is I1. Similarly, if we apply the junction rule to the junction on the right, the current flowing into this junction is equal to I1, and that has to equal the current that's flowing out of the junction, which is I2 plus I3. Notice that when we apply the junction rule to these two junctions, we get the same equation. And that's one important thing to understand about the junction rule and the loop rule, is that if we consider this example here, I have three different currents that I'm trying to solve for. So there are three unknowns. However, there are two junctions, and it turns out there will actually be three loops. So that means that the junction rule and the loop rule will give us 5 equations. So the junction rule and loop rule will always give you more equations than unknowns. And the reason that that happens is that some of these equations are going to be either identical, or you could write one of the equations by adding or subtracting to the other. So now let's take a look at the loop rule for the circuit. Remember that the loop rule says that the total voltage change around any closed loop in a circuit must equal 0 volts. It turns out that for this circuit there are 3 closed paths that we can go around. One of them is this bottom path right here. So if I imagine starting at the bottom right corner and going around this, well, as I go over the battery, remember that the long end of the battery is the positive side of the battery. So I'm going from the negative side to the positive side, so I gain 12 volts. So first we gain 12 volts when we go over the battery, then I go around the wire up here. Now notice that when I go over this resistor, I'm calculating the voltage change as I go in this direction, but the current is flowing from the right to the left. So that means we're going to gain a voltage that's going to be equal to I2 times the resistance, which is 5 ohms. So the total voltage change is going to be equal to 12 volts plus I2 times 5 ohms. And because that's the voltage change around a closed loop, Kirchhoff's law tells us that this has to be equal to 0 volts. So actually right away we can see that we've guessed the direction of the current I2 wrong. If we take a look at another loop, so another loop we could look at is the loop going around the outside of the circuit, so going all the way around like this. So again, as we go over the battery, we're going to gain a voltage of 12 volts, so we get plus 12 volts. And notice now we're going across this resistor in the same direction that the current is flowing. So that means we'll lose voltage as we go across this resistor, and then we'll lose voltage again as we go across the second resistor. So we'll have minus I1 times 10 ohms, and then minus I1 times 5 ohms. And then from there I can go all the way back to my start point without going over any resistors or batteries. And remember that whenever you go all the way around a loop, the loop rule tells us that the total voltage change has to equal 0 volts. And the last loop that we could look at is I could just go around this top part of the loop right here. So let's go ahead and start from this bottom right corner again. So now, as I go around this loop, I'm going to go through this resistor in the same direction that the current flows, which means I'm going to lose some voltage as I go across this. So we're going to have minus I2 times 5 ohms. And now I'm going to go across these two resistors in the same direction that the current is flowing through them as well. So we'll have minus I1 times 10 ohms, and then minus I1 times 5 ohms. And since we've gone all the way around a loop, this has to be equal to 0 volts. So let's take a look at another example. In this example, we're given a section of a circuit, and we're asked to find the current that flows through the top part of the circuit, the bottom part of the circuit, and this right half of the circuit. And then we're also asked to calculate the total voltage difference across the whole thing. So if we look at this circuit, there are two junctions. There's a junction on the left and another junction on the right. And the junction rule, remember, says that the current that flows into the junction has to equal the current flowing out of the junction. So applying the junction rule to the junction on the left, we can see the current flowing in is equal to 10 amps, and the current flowing out is equal to current 1 plus current 2. If we apply the junction rule to the junction on the right, we can see the current flowing into this junction is equal to I1 plus I2, and this has to equal the current flowing out of the junction, which would be I3. Now if we look at these two equations together, we can actually see that if we combine these two equations, so this first equation says I1 plus I2 is equal to 10 amps, the second equation says I1 plus I2 is equal to I3. So we can see current 3 is just equal to 10 amps. And hopefully you can just see that right away. If I have current flowing in from the left that's 10 amps, and then it goes through these two branches and comes together and flows out the right end, then the current flowing out the right side of the circuit also has to equal 10 amps. Now, since we started out with three unknowns, I1, I2, and I3, we're going to need three equations to solve this. Now we found two equations by applying the junction rule. To get the third equation, we need to apply the loop rule to this segment of the circuit right here. So if we go around this loop in a counterclockwise fashion, going around like this, so if I start at this corner, because I'm going in the opposite direction that the current flows through this resistor, I'm going to gain a voltage that's equal to I2 times 8 ohms. And then as I go through the top half of the circuit, I'm going to be going across these resistors in the same direction that the current flows. And remember, voltage is lost when you go over a resistor in the direction the current flows. So here I'm going to lose a voltage that's equal to I1 times 10 ohms, and then I'm going to lose a voltage over this resistor that's equal to I1 times 14 ohms. And then that takes me back around to where I started, and remember that the total voltage change around any closed loop has to equal 0 volts. So all of this is going to be equal to 0 volts. And if I want to, I could simplify this a little. This is going to be equal to I2 times 8 ohms, and then I can combine these two because the current flowing through the two resistors is the same. So this is equal to I1 times 24 ohms, which is basically the same as treating these two resistors on top as a single equivalent 24 ohm resistor. So at this point, if I want to, I can solve for I2 in terms of I1. So I can write I2 times 8 ohms is going to be equal to I1 times 24 ohms. And then if I divide both sides by 8 ohms, I can see that I2 is going to be equal to 3 times I1. So this is the equation that I get from applying the loop rule. So now if I combine this equation that I got with the loop rule with one of the equations that we get from the junction rule, for example, we have that I1 plus I2 has to equal 10 amps. That was the equation we got from the junction rule over here on the left. I can combine these two equations, so I can plug I2 into here, so we see that I1 plus 3I1 is equal to 10 amps. So I1 is going to be equal to, so here we got 4I1 is equal to 10 amps, so I1 is equal to 2.5 amps. And since I2 is equal to 3 times I1, I2 is going to be equal to 7.5 amps. And so the last part of this question asks us to calculate the total voltage difference between side A and side B. And so all we really need to do is we need to apply Ohm's law to either one of these two paths, because the voltage drop across I2 has to equal the voltage drop across this top part of the segment as well. So if we look at the bottom half, we have I2 times 8 ohms is going to be equal to the voltage drop between A and B. So I2, remember, was equal to 7.5 amps, and if we multiply that by 8 ohms, we can see that the voltage drop is going to be equal to 60 volts. Alternatively, we could calculate the voltage drop across these two resistors over the top, and we should wind up with the same thing. In fact, we could check that. The voltage drop across the top part of the loop is going to be equal to I1 times, and the total resistance between these two ends is going to be 24 ohms. And that's equal to 2.5 amps times 24 ohms. And again, if you plug that into a calculator, you'll see that this is going to equal 60 volts as well. So we get the same voltage drop across the top part as the bottom part, and of course we should get the same voltage drop because the ends of this, the left side are connected together, and the right sides of these are connected together. So it's kind of like resistors in parallel, so the voltage drop across them will be the same. And at this point, I think I'd like to end this discussion on the loop rule and the junction rule, and in the next video, I'm going to talk about how we can actually measure the voltage difference across different parts of a circuit or the current flowing through a circuit.